Recording. So today we are moving on. I do have quizzes to give back to you. I'll give those back a little bit later. We're going to start talking about circles. So pretend that looks like a circle. I know my drawing sucks. Some features of a circle. The two defining features of the circle.
Inside and outside.
One is the location of the center. And two is the radius. The technical definition of a circle is the set of all points equidistant or the same distance from a given point. Well, that given point is the center. That distance is the radius. So those two features completely define our circle. However, there are a lot of other features of a circle that we use that are very useful. One of those that many people don't realize, but it's very common, is a line segment where the ends are on the circle. That is called a chord. This is actually a way more common application than you might think. Now we have a chord that contains the center is called what? Diameter. There you go. This brings us to our first relationship. The diameter, which we're just going to abbreviate with D from now on, is equal to 2 times the radius. So in other words, D is equal to 2R. Is that formula? Another feature of the chord is of the circle is a perimeter. That is referred to as circumference. Circumference is just the perimeter of a circle. It's just the special name for it. Now, to find circumference, we actually need to find a constant that is used in circles, and that is this thing, which is called what?
Pi.
Pi. Pronounced pi. And it is equal to the ratio of the circumference of a circle divided by the diameter of that circle. And it typically comes out to 3.1415926, blah, 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 blah. We will typically use 3.14. Now, many of your calculators have a pi button on them. You can feel free to use that as well. I will give you a little bit larger answer. But on any quizzes or tests, I will use 3.14, and then I'll also use the pi button. Any answer in between the two will be acceptable. Yes, Avery, any question?
Or not, I was going to ask about shortening like that, but then you got to it before you could ask.
Sure. So, often we don't usually know the circumference and diameter and divide it to get pi. Typically, we know one or the other, and we want to calculate the other from it. So the circumference, abbreviated C, is equal to pi times the diameter. That's one formula for circumference. The other formula for circumference is, since the diameter is 2 times the radius, 2 times pi times the radius is another way. It's the same thing. 2 times the radius is just the diameter. It's a math grammar thing, by the way, that we put the 2 first instead of saying pi times 2 times the radius. It's a math grammar thing that the numbers always go first in those expressions. To me, it'd make more sense if it's pi times 2r, but that's just the way it is. There are other features of a circle. One is the area discussed. Area, we actually looked at this last week, how the area is chopping it up and turning it into a rectangle. Area of a circle is pi times what?
Radius squared.
Radius squared. So if I have a circle with a radius of 4 inches, area is pi times 4 squared, otherwise known as 50.24 inches squared. How about the circumference of that circle? That would be 2 times pi times the radius of 4. 2 times pi times 4, 25.12. Now that's just the length, that's just inches. Have a circle, and that looks like it goes through the center. The diameter of 10 feet. How would I find the circumference of that?
Pi times 10.
Pi times 10 feet. That is already a diameter, so we use, instead of 2 times pi times radius, we just use pi times diameter. Pi times 10 is 31.4 feet. What if I want to find the area? Pi times, maybe 10 squared, it's going to be, yeah. Diameter is 10 feet, the radius is 5 feet, so pi times 5 squared. 78.5 feet.
Because isn't the radius just half of the diameter?
Other parts of a circle that are a little bit lesser known. Something called a secant. A secant is just a line or a segment that contains points inside and outside of the circle. So that is a secant the way I have it drawn there, but we're more used to seeing a secant like that where it continues on through the circle. Another form of a secant could be just a commonly used form of the secant that starts at the center and goes out. That is a secant. The radius, of course, would stop at the circle. The secant would keep going to get points outside of the circle. Tangent. What does the word tangent mean? Tangent touches the circle at exactly 1 point. So it only contains 1 point on the circle. All the other points are outside the circle. Some features of the tangent are going to be useful to us. If I have a radius of that circle that goes out to the circle at the point of tangency, that radius and that tangent form a right angle. Now in this class, we don't get into trigonometry, but in trigonometry, right angles are a big deal because they form right triangles. So finding those right angles help you to form right triangles to use your trig. Again, I repeat, just to relieve any stress, not going to use trig in here if I get that far.
Nice.
To define this next feature, I have to define another one first. This line across here, of course, is a diameter. That's what we often refer to as a reference diameter. Generally, it's a horizontal diameter across the circle. Every point on that circle then has a feature called a sine. The sine of a point is the distance from that point to the reference diameter. So the sine of this point is that distance. Of course, remember that distance is measured at a right angle. Distance from a point to a line is always measured at a right angle. So this point has a sine. This point has a sine. It's like that. This point has a sine that goes that way. These three are said to have positive signs because they're above the reference diameter. This one is said to have a negative sign because it's below the reference diameter. Now, where else do we see the word sine? Said we're not going to do it in this class, but we see sine when we talk about trig. Most people think trig is about triangles. Trig gets applied to triangles, but it comes from circles. If I have a circle, that's my reference diameter. This portion of the reference diameter, that half of the reference diameter, is what's referred to as initial side. Angles then are measured from that initial. We talked about rays being a direction. Well, this is how the direction is. That's the 0 degree direction, that initial side. Angles then are whatever are formed going around counterclockwise. So let's say this is 35 degrees. That angle defines a point on the surface of that circle. That red dot is the point defined by that angle. That point has a sine. Guess what? The length of that sine is the sine of 35 degrees. That's what defines our trig function called the sine. Notice there's other trig functions called tangents and secants. They also come from those features we defined up above. I'm not going to get into it here. Like I said, we're not going to do heavy trig in this class. But it's kind of interesting to realize that those trig functions are found on a circle. They're measurements that you actually take off the circle. Then they get applied to triangles because they're similar. If we get a little extra time, I might show you some of that here by the end. So if I have my circle and I have two radii, plural of radius is radii. Those two radii form an angle at the center of the circle. That angle is called central angle. That central angle is very important because what it does is it actually defines a fraction of the circle. If I have, let's do this. I have this. My central angle, call this 63 degrees. I can find this pi wedge here is called a sector of a circle. We typically just call it a sector. We imply that if we're talking about sectors in geometry, we're talking about circles. There are sectors in other applications like mapping space and stuff like that. But for geometry, it's always on a circle. But that sector of a circle, if I want to find the area of that sector, it is found as a fraction of the whole circle. Well, what do I mean? Well, if I wrapped all the way around, how many degrees would that be? 360. This sector is only using how many degrees? 3. So this angle, this sector, is 63 360ths of a circle. So how does that help me find the area? Well, I can find the area of the whole circle by doing what? Put all the letters in there.
Getting the diameter, or,
Area would be pi times, I need the radius, right?
yep, r squared.
So I tell you that radius is 8 inches. Pi times 8 squared, right?
Yep.
Gives us what, 200.96 square inches? That's the area of the whole circle. Now that's if I use pi as 3.14. If I use the pi button, it's at 201 point something. So how do I find the sector area? Well, the sector area of the whole circle, times that fraction, 63/360. Sector is that fraction of the whole circle. .96 times 63 divided by 360. Notice I don't have to put in a fraction. I just multiply by 63 and divide by 360. Okay, 35 point, we'll round that to 17. That's 35.17 square inches. That is the area of this highlighted piece of that pi wedge there. Because it's just a fraction of the whole circle. Well, since we're talking about central angles, let's talk about another thing central angles can be used to find. It not only cuts out a section of the area of the circle, it also defines a section of the circumference of a circle. That is called an arc. The arc length is also defined as a fraction of the whole circle. So we find the circumference of the whole circle would be, of course, let's put in a 4-foot radius here. How do I find the circumference? 2 times
Pi squared.
pi
Or pi.
times the radius.
Yeah.
Right? Gives me 25.12 feet circumference. Well, how do you think I'm going to use that then to find the arc length?
A equals 1.
Well,
75/360ths of 25.12.
perfect. I take that whole circumference of the whole circle, and I'm going to find 75/360 of it. 3/60ths of it. Yes, 25.12 is my circumference, times 75 divided by 360. It's 5.233 feet. That is the length of that arc. Not so bad.
Better than a shark stick in the eye for a shark. Sharp stick in the eye, that's what I meant to say.
So let's say this is 64 degrees. That is a central angle. I will indicate this is the center of the circle. We know that this arc here is 64/360ths circle. We often will define that arc to be a 64-degree arc. If we don't know the radius, we can at least say it's 64 degrees, telling us that it's that fraction of the whole circle. Once we have the radius or the circumference, we can then find it from there. Bless you. This angle formed here is what is referred to as an inscribed angle. Inscribed means inside a circle, or on the circle. The vertex of that angle is on the circle. there is a very, very direct relationship between the size of that angle and the size of the arc out here. It is exactly half. How can I demonstrate that that is so? Well, do this. Pretend that's the center of the circle. And let's just call this 40 degrees. All right. Now, we're going to extend this over to be a diameter, and we're going to connect this here. What do I know about this length and that length?
The distance.
They're the same. They're both a radius of the circle. The radii in the same circle. So they're the same. Now, one rule we did not talk about in triangles is this. Let's say this is 12 inches, 11 inches, and 8 inches. We call these angles A, B, and C. Which angle has to be the largest, A, B, or C? Which angle has to be the largest, A, B, or C?
B.
Why would I say B?
Oh, the angle.
It's opposite the largest side, right? The biggest angle in a triangle, the largest angle has to be opposite the largest side. Which angle has to be the smallest?
Angle A.
Angle A, because it's opposite the smallest side. If I have a triangle, it's isosceles. What's isosceles mean?
No side is the same.
Two angles are the same. Scalene means no side's the same. So those two that have a single hash are the same. What does that mean about this angle and this angle?
Those are the same.
Yeah, because if one of them's bigger, it has to be opposite a bigger side. So if they're opposite sides that are the same length, the angles have to be the same. So going back to this picture, this angle and this angle have to each be the same. Well, we also know that this angle here has to be how big?
180 minus 40.
Yeah, that's a line across there. So those two angles add up to a line.
Is 140.
Which is 180. So we do 180 minus 40 is 140 degrees.
And those other two.
Well, what's a triangle have to add up to?
180.
180. So that means these three angles have to add up to 180, which means
The other two are 20.
180 minus 140 gives us 40 degrees. And since those two have to be equal, we divide it by 2. That's 20 degrees. That's 20 degrees. Well, that just affirms our relationship here that 20 is half of the 40. Because this would have been a 40-degree arc out here because it has a 40-degree central angle. So the central angle is equal to the angle of the arc. The inscribed angle is half of the angle of the arc. If chords intersect, they do some really interesting things. Space there. First thing with intersecting chords is they cut each other into predictable piece sizes. What do I mean by that? Well, let's say this piece here is 4 inches. This piece here is 3 inches. This piece here is 9 inches. That piece is X. So these chords intersect, and what I'm saying is this one gets cut into 2 pieces. This one here gets cut into 2 pieces. The pieces of the 2 chords multiply to make a predictable product. What I mean by that? Well, 4 is in the same chord as what other piece? 9. So 4 inches times 9 inches has to equal the product of the pieces of the other chord that intersects. So 3 times X. So I could probably get rid of the units, but 4 times 9 is 36 equals 3x. And then, of course, to solve for x, I'm going to divide by 3. 12 equals x. So yeah, this has to be 12 inches. So intersecting chords cut each other into pieces that have the same product. This is a very useful thing if you're doing an arch. Let's say you're doing an arch here. The width of this arch might be 36 inches. And the height of this arch, let's see here. Let's say this is just 6 inches up. Whether this is a arch on the top of a doorway or whatever, arch on the top of a window. How do we know how to create that arc for that arch? Well, the easiest way when you're doing construction to draw out an arc or an arch is to find where the center of that circle would be. Take a piece of string that's that long, put the pencil at the end of the string and just sweep it around. It draws a circle. Simple way to draw a circle is always just to find its center and a piece of string and a pencil. Hold one in the center and strike the arc, they call it. But to do that, we would need to know radius of the circle, right? How do I find the radius of that circle? Well, let's draw this out as a small circle. Cut this across here. This piece is 6 inches. That chord here it gets cut in half. So what's half of 36? 18 and 18. Well, we can use what we just learned to find this distance x. It's 18 times 18. That's the two pieces of that chord. Has to equal 6 times x. Two pieces of that chord. What's 18 times 18? Say 324.
324.
And then what do I do?
Divide by 6.
Divide by 6. It's 324 divided by 6. 54. X equals 54. So now what is the diameter of that circle? 54 plus 6. 60. Radius would be half of that, 30 inches. So we have 30 inches here. So we know if we find the center of the circle, and it's easy to find the center. Once you do to find the center, you know that one end of the arch is over here, right? You take that 30-inch string and you strike an arc. Now the other end's here, you take that 30-inch string and you strike the arc. Where the two arcs intersect, that's the center of your circle. Then you reverse it, anchor the string here, take your 30 inches, and you draw the arc for your arch. It's a very common construction application. Arched fireplaces. When a stonemason builds the form for inside that fireplace, that's how they figure out how wide the fireplace is, how high they want that arch to be up, and they can find the radius of the circle and draw out their circle and create their forms for it.
And that's the best way to do it. There's no
the best way.
tools.
That's the quickest way to do it, yes. I mean, there's shortcuts formula. Instead of 18 times 18 equals 6x, they have a shortcut formula. 18 times 18 divided by 6 equals x. Then you still got to go through and add them together. Other cool thing about intersecting chords. Obviously, we know from what we talked about for angles, this angle and this angle have to be the same. They're those vertical angles by intersecting lines. This arc here, let's say that is degrees.
That one's double.
This arc over here is not necessarily double, but let's say it is 94 degrees. We now know these angles. Let's think about it. If those chords were diameters, if they intersected at the center of the circle, these two arcs would be the same, right?
Yes.
And this angle would equal that arc, this angle would equal that arc. As we move that away from the center,
one
So
gets.
this one gets bigger, this one gets smaller. The angle stays the same though. So this angle is just the average of the two arcs. I take 94 plus 22 and divide that by 2. Well, 94 plus 22 is 116, right? Divided by 2 is 58 degrees. It's a 58-degree angle. Homework 39 is the homework that deals with circles. We might have to go over some of this tomorrow. I realize I don't have an answer key out there for the homework, so it's kind of frustrating for some of you. So at the beginning of class, don't be afraid to just yell out if you want me to go through some of the problems. I think there's still a couple of topics on circles I missed today, so we'll probably have to go through some of them tomorrow anyway.
I think he fell asleep.
That's fine.
Yeah, he's out.
I'm gonna stop the recording here for this part. I will be gone.